This spreadsheet is a simulation of operating one of those big power generating wind turbines. You want to keep them, for some of them, you want to keep them near a constant speed even when the wind is speeding up and slowing down, because it works better with the power grid that way. So here I've got a big simulation, bunch of columns tracking what's happening every 0.05 seconds, and 400-second time span here. And the wind starts out steady, but then speeds up and stabilizes and then slows down again and then has a little blip. And we're trying to keep this curve, the reddish curve on top here, as roughly constant as we can. That's the speed of the blade rotation. The way we change the speed of the blades compared to the wind speed is by tilting the blades a little bit. It's also called feathering in some contexts. So we have to decide how quickly do we want to tilt the blades. Remember, the whole thing is spinning like this. Usually 3 blades rather than 4, but that's how my arms work. So we can change these green cells here to make ourselves more or less aggressive in tilting those blades. And we want to keep these orange cells as small as possible. These orange cells tell us how good we're doing at keeping the speed of the whole rotation roughly constant. And this orange cell is about how much effort we're putting into spinning the blades, because the more you use your motors to spin the blades, the sooner they wear out and the more maintenance you have to do. So there's some trade-offs there. So let me know if you're interested in looking into this as a project or as a homework. Which one is it? Simple, hard? It's kind of interesting. Here's an optimization related to wind turbines. When you change the pitch angle of the blades and the wind is going at different speeds relative to how quickly the blades are turning, you get different power coefficients, like efficiency basically. And so this graph is at a bunch of different blade angles, and this is TSR, tip speed ratio. And you get this graph by doing a bunch of really complicated physical simulations that are way above my head. But my question is, can we fit a nice function to this and then use that in a simulation of this whole control system? This graph is kind of a simplified version of that, but the optimization problem I'm talking about here is fitting a function to this data set, essentially, because there's no nice function that determines this. It's a really complicated simulation. I've been in communication with a bio/chemistry lab at Eastern that's trying to figure out how cells behave in response to different chemical environments. So they're looking at yeast, and here's an electron microscope picture of a slice of a yeast cell. And they're looking at the vacuole in the yeast cell, which is outlined in red here. Maybe it's hard to see. And then they want to know about how many autophagic bodies there are inside the vacuole, and those are outlined in green here. That might be even harder to see. So this set of red and green lines was decided by, I think, a grad student just sitting there and outlining what they see on an image. But it would be nice if we could train a machine learning sort of model to do that outlining for us automatically. That would be more objective and faster. So let me know if you're interested in this. Here's a data set sent to me by one of our EMU geography and geology professors. He's working on groundwater levels. This one is near Madison, Wisconsin, but could be anywhere. So the graph you're seeing is the amount of water in a test well day by day or hour by hour, actually maybe even minute by minute. And you can see it's got this strong up and down pattern. That's because there's another well nearby that the city is using to draw water up out of the water table and into their municipal system. So let's see a zoom in of it here. So the idea is to try to fit a differential equation system to this to predict where it's going to go next and what happens when the pump turns on, what happens when the pump turns off. And that differential equation system can tell us something about the groundwater flow in that area. Of course, I've started us with the nicest of the graphs here, but we can look at some of the others. And those don't always look as nice, and so we can ask, is the optimization method that we use for some of these nice graphs going to work for some of these not so nice graphs? So if that's a project that's interesting to you, let me know and we can talk about it. In some classes, to determine when my office hours should be, I've surveyed my students with an online poll, and they go and indicate for each time block that I've listed as an option whether that would be okay for them or not. There's a sort of if need be kind of a response as well. So here's some data from some survey kind of like that. And the idea is how, if you had all this data on student preferences, how would you schedule your office hours? You would want to do things like have the maximum availability to students, or not offer so many office hours you just tire yourself out. All kinds of interesting things to think about there.